Okay, hello. I'm going to be working out what is the minimum height that a roller coaster has to start at in order for a car to get around a loop-de-loop at the bottom. And thinking about energies, what this really depends on is, does it have the necessary velocity at this top, which in terms of energies means, does it have the kinetic energy at the top to make it around, which is all dependent on the kinetic energy at the bottom of the loop-de-loop, which is dependent on the GPE to start with, which is dependent on the height. So that's how we're going to link it all together. Now, the GPE at the top is just mgh, and the kinetic energy at the bottom is also mgh, because kinetic energy at the bottom equals GPE at the top. So but now we're going to look at the KE at the top of the loop-de-loop, or the minimum KE that you need at the top of the loop-de-loop to make it all the way around. And that's going to equal the KE at the bottom of the loop-de-loop, or sort of the initial KE, minus whatever KE it loses getting to the top, which is equal to the new GPE at the top, because the kinetic energy is transferred into GPE as it moves up the loop-de-loop. So that means that the KE at the top is the KE at the bottom minus the GPE at the top, 2mgr, or mg 2r being the height of the loop-de-loop. Now, another way of expressing the kinetic energy at the top is also just KE equals half mv0 squared, where v0 is the sort of minimum velocity that it needs to make it around the top. So now we're going to equate these two and just get this expression of half mv0 squared equals mgh minus 2 mgr. And now, to actually sort of reduce the variables of this whole thing, we can, what we're going to first do is look to get rid of this v0. Now we're going to have to go to circular motion for that, and thinking about the car at the very top of the loop-de-loop here, with the car mass m at the very top, it's going to have a centripetal force of the reaction force on it by the rails of this track plus its weight being mg. So that's the centripetal force. So the equation for centripetal force is F equals mv squared over r, r being the radius. That's the equation for the centripetal force in circular motion. And the centripetal force here is r plus mg, so we're just going to do r plus mg equals mv squared over r. Now that's just the simple equation for the centripetal force. But what we want to actually do is work out the velocity at which the reaction force disappears, because that's just another way of saying, when does the mass lose contact with the rails? You know, at what velocity does it just fall off because it's not moving fast enough? And how we're going to do that is just do r going to 0, because there's not going to be a reaction force if you're not touching it, and it's just, therefore, just mg equals mv0. Now we're using the v0 because we're talking about minimum velocity needed, you know. What's the velocity where r is 0, which is going to be v0. We get this expression. We just cancel out the m's here. It's just g equals v0 squared over r, or v0 equals root gr. So, is that focused? So we can now sub in that v0 back into the original equation, and we've now taken away one unknown and actually just added two unknowns that were already in the equation. So we're just reducing the number of variables. So it's now half m root gr squared equals mgh minus 2 mgr. Now the bulk of the theory is sort of out the way. What we can really do is just flat out algebraically solve this, right? Half mgr, because it's a square root that's just being squared, equals mgh minus 2mgr. Now let's just cancel the m's, cancel the g's. Half r equals h minus 2r, or h minimum equals half r plus 2r equals, what is that, 5 over 2r. So apparently the minimum height, starting height of a roller coaster has to be 5 over 2 times whatever the radius is of the loop-de-loop that you want it to get around.